Hi everybody, welcome to another IZ8 DWF arcade repair video. I've got a complete board set of the Supershot Arcade game made in Italy by Model Racing. So here we have the main CPU PCB, which is the biggest one of course. And it looks in very good conditions too. This small PCB just makes some incandescent lamps blink at every good shot. And this is the Audio FX PCB. Together with all the boards, I've also got the power supply transformer, a magnetic ballast for the fluorescent lamps, and all the wiring harness with game controls and all the lamp sockets too. As always, the first repair step is a good visual inspection of all PCBs. In these old boards, I often find cracked or broken ceramic capacitors, like the one in the picture. These, of course, must be replaced. Another very common issue is oxidized edge connector pads. It's always a good idea to at least make a fresh thin layer on the power supply pads that carry high currents. I have showed several times in my arcade repair videos how to restore the thin layer on the edge connector contacts, so if you are interested, check the old videos in the arcade repair playlist. The big electrolytic capacitor on the 5V regulator input can be tested in circuit, and luckily it's still good. Another issue on this CPU PCB is this heatsink that needs tightening. This other one looks okay. On the audio PCB, this film capacitor mounted on the solder side is broken. Its color code indicates a 10 nanofarads value, so it was replaced with a smaller film capacitor of the same value. I'm going now to check the power transformer. As you can see, this one has quite a lot of different secondaries, including the ones needed for the video monitor. I want also to determine the correct mains input switch, since it's not labeled on the chassis. I'm going to check the highest voltage secondary, which is the 38 volts one that powers the monitor chassis. So let's switch on. Okay, we have more than 42 volts on that secondary. So let's flip the voltage select switch. That's better now, almost 39 volts, but it's without any load. Now that I checked it, I added a temporary label on the main select switch. Luckily, all edge connectors have a red dot to avoid plugging the board inverted. The only white connector was used for the flasher board. However, it's always a very good idea to check if the soldered wires match the position of the routed pads on the PCB. And when in doubt, I can also double check on the wiring diagram anyway. The main CPU PCB also gets a few AC voltages directly from the power transformer, so I've checked that its connector is the one with the big wires coming from the power supply chassis. Then I've installed a small incandescent bulb on one socket, so I can verify that it flashes when I hit a target during a game. And since the flasher PCB gets the mains voltage, I decided to put it into a plastic bag to avoid it touching anything else on the bench. As always, the first thing to check is that every regulated DC supply has the correct voltage. In this game, all DC regulators are on the main CPU board, and for sure the most important one is the plus 5 volts rail. It showed about 3 volts, so I have powered the board off without even filming it. We now need to troubleshoot the circuit circled in this picture. This is the input voltage to the 5-volt regulator, and it's too low. Now, the input voltage to a regulator could be too low in case, for example, a dead short is sinking too much current. But if this was the case, and assuming that for some reasons the fuses don't blow up, for sure the diodes would overheat very quickly, and the regulator plus the bypass resistors would overheat too if the short was on the output side. However, everything remains cold in this case. So this is one AC phase measured before the rectifier. The positive wave seems like clumped, and the other one looks just the same. So I decided to check the power transformer with a 12-volt lamp as a load. And this phase looks good, 9.5 volts is okay. And the other secondary tap is okay too, so it must be some wiring problem. And indeed, on the power connector, the center tap wire was barely making contact, and I could pull it out without any effort. So, since I don't have the correct tool to crimp the wire to a new contact inside the connector, I've opted to temporarily solder a wire to the fuse holder of the 10 volts center tap. After restoring the 5 volts rail, the monitor showed something, or at least it tried. But as you can guess, it wouldn't sync to the video signal output of the board. Now, the vertical rolling could be corrected with the vertical hold control on the monitor. However, the horizontal scan frequency would never lock to this video signal. Measuring the horizontal frequency showed that it was way higher than the usual 15-point-something kHz typical of both American and European video formats of that time. At first I thought there was surely a fault somewhere in the frequency divider chain of this board. As usual on these old games, all video and CPU frequencies are generated by cascaded dividers from a single crystal oscillator. In this case, the quartz is cut for 11.289 MHz. Following all divider chain showed no faults, however. The only tricky part of the divider chain was this one. That's exactly where the horizontal video sync signal is generated, so let's try to understand how it works. The 74LS161 counter is reloaded after overflowing from the value 15 back to 0. However, the reload value is not fixed. 3 bits can be either 0 or 1, depending on the output of the next stage. Only the second MSB is always 0. So the counter is reloaded first with value 0, and on the second overflow it is reloaded with value 11. Since this counter always counts up, when starting at 0 it takes 16 clocks to overflow again, and when loaded with 11 it only takes 5 clocks to overflow. So the circuit is dividing the incoming frequency by 21, and that confirmed that indeed the horizontal frequency was meant to be 16.719 kHz. Clearly, I need some different monitor, and in this case I tend to look at old computer video formats, since I still have some of the old monitors. One good candidate could be one green phosphor monitor that I used in the early 90s, connected to a 386 PC that only had an EGA card. So that monitor for sure could sync to a horizontal scan of almost 22 kHz. But those old monitors had TTL inputs, so I need first to identify where on the divider chain I can get suitable scan signals to feed the TTL connector. In this picture, I identified the positive horizontal pulse and negative vertical pulse needed to imitate an EGA signal. Then the positive TTL video signal can be obtained just before the resistor summing point that goes to the original composite output. So I soldered a few test connectors to the appropriate IC pins to bring the needed signals to the EGA input. And yes, that worked well. I can see what's going on finally. Now, after power on, the game appears stuck, always with this image. No button seems to have any effect. Looking at the dip switches, we notice that number 3 should activate a reticule to help in setting the aim. And indeed, flipping that switch and resetting the main CPU gives this reticule screen. Moving the aim potentiometers also moves the white square across the screen, so a good part of the board must be working fine. Notice, however, that flipping back the switch number 3 returns to that stuck screen, and this always shows credits higher than 0. So, after scratching my head for some time checking various signals with the logic probe, I decided to have another look at the connection diagram and the schematic to understand why the game would think it had credits. And I finally noticed that the coin input goes to the audio PCB, which I had left unconnected, thinking that I would first check the main CPU board alone. To make a long story short, we cannot troubleshoot this game without the audio PCB connected. And in fact, with the audio PCB connected, the game attract mode runs and it shows no credits. Now, pressing the credit switch makes the game get a credit and freezes the attract mode. The game can also be started, so far so good. However, with the pair potentiometers it's not easy to hit a target. We can hear the lamp relay clicking whenever I hit the target. But we cannot hear any audio effect from the speaker, so that will be the next thing to troubleshoot. Since all sound effects are missing, the first thing to check is the presence of the power supply voltages on the audio PCB connector. Here we have a problem. This should be 11 volts, but we get less than 1 volt. This one instead looks okay. This unregulated DC rail comes from the main PCB and is made with a simple bridge rectifier plus a capacitor. And a quick check showed that indeed there's no voltage output on the bridge rectifier. Another long story short, tracing the connection from the power transformer secondary showed no continuity across the fuse holder. The fuse inside was not blown, but for some reasons is shorter than the correct size that fits in that holder, so the fuse was replaced with one tall enough. So let's see what happens. Well, we definitely have sounds now. But it seems that the beer glass hit sound is not working. Back in the old days, every sound effect was made with a dedicated and often clever electronic circuit, most of the time combining analog and digital components. The beer glass explosion sound of this game is a very good example of that lost art of electronic design. The circuit, circled in red, is basically a sound oscillator with separate attack and decay times and modulated with a signal obtained by scanning a small TTL prom whose outputs are converted to analog signal by a weighted resistor DAC. To illustrate every detail of this circuit, I would probably need an entire half an hour video. One suspicion I had initially was that maybe the TTL prom was defective, so I tried uploading a dump of it to the Romident website, and luckily it matches the dump of another shooting game. By the way, I've uploaded the first known prom dump of this game audio PCB. So first of all, let's see if the sound effect is triggered by the CPU board. On the logic probe flashing clearly shows that the sound is enabled when I hit a beer glass. The oscilloscope shows some kind of signal at the output of the sound circuit. But we're not hearing anything from the speaker, that's weird. Then I noticed the output coupling capacitor has a missing shoulder, but I could measure it in circuit and it seems good. Anyway, I decided to replace it, and one leg detached itself from the body as soon as I tried to remove it. By the way, these capacitors are commonly called tropical fish because of the color code value on their body. These were made by Philips or Mallard, if I remember correctly. I've replaced it with a green body film capacitor because this audio PCB already has other capacitors of the same type, so this replacement also has the right aesthetic. Of course, that didn't fix the missing sound, and I decided it is not possible to troubleshoot this circuit by starting a new game every time, wait for the beer glass screen, and trigger the sound 3 or 4 times with one hand, and then restart the game again. So let's see how we can interface directly to the sound PCB and trigger the right sound continuously. First, of course, we need to provide some power supply voltages to the board. Luckily for this particular sound, only the +11 and +5 rails are needed. Then we must connect to the appropriate pin and inject a series of TTL pulses to trigger the sound continuously. This task will be accomplished by a function generator. We must also provide a TTL high signal to pin 14, which is the main audio-enabled signal. I will simply connect this pin to the 5V rail. And last but not least, connect a speaker to the sound output pins. So the power supply is connected. The function generator is set for 300 milliseconds pulses at a rate of 2 times per second. That should do. At the speaker we can actually hear some audio effect, but it's too low and not correct anyway. These are the prom output resistors. We have pulsing signals here, which is okay. Now I really looked at almost every corner of this circuit, but I didn't really find a point with a missing signal. Then I finally had one idea. Signals are there, but probably something is working at the wrong frequency. There is a dual timer IC as part of this audio effect. The lower timer is used as oscillator to clock the address scanner for the prom, and the upper timer is generating the actual sound that gets modulated. So probably one or both the timing capacitors have failed or drifted too much. And by the way, one of them also has a missing side, which is not a good thing. So again, one tropical fish was replaced with a film capacitor of the green kind. And that did the trick. Finally, we have the good sound effect, and this volume can be regulated by this trimmer. Now, by visual inspection, all tropical fish capacitors with a value of 100 nanofarads or 47 nanofarads had some missing or cracked sides, so for the board reliability, I decided to substitute them all. Notice that many of them could not be removed without some leg detaching. All other tropical fish capacitors with different values looked perfect, with no cracks, so I left them in their places. This is a picture of the board after the substitution. Some of the green capacitors, as I said, were already present. The game now has the correct sound again. As we have seen before, the game can draw a reticule to help in correctly setting the aim. The horizontal movement appeared to be smooth with no jumps. However, on turning the vertical potentiometer, I noticed the white square making large jumps, often right outside the grid area. Clearly, there's more work to do before I can call this job done. The first thing to do is connect a multimeter across the vertical potentiometer so I can see if the resistance value moves smoothly or not. And indeed, this is the problem. The value is not varying smoothly and we can observe sudden jumps of several kiloohms. I hope the potentiometer is just dirty and can be cleaned, but first I have to remove it from its mounting harness. The gear was fitted to the shaft with two screws, one passing through the shaft itself and one passing laterally to it. Once the potentiometer is free, we can lift 4 tabs that hold the bottom shell to the upper body. And indeed, on the inside, we notice lots of carbon debris that detached from the rail during countless hours of rotations. And finally, the carbon rail must be carefully cleaned with cotton swabs and isopropyl alcohol. Now the resistance value can be changed without jumps. So far so good. And the end cursor can be moved on both axes without jumping even a single square. That's how it should be. The last PCB of this board set that I'm going to check is the cabinet lamp flasher. Basically, it just makes some incandescent bulbs flash whenever the player hits a target. I really know it works because I could hear the relay clicking, but for safety reasons I've run the game without connecting the mains wires going to this PCB. And yes, the small lamp I've used is happily flashing. Now notice that this very low wattage lamp is showing a faint glow as long as the game is powered on. This is a nice trick to avoid burning lamps too quickly. In fact, observe this resistor-capacitor series that is connected in parallel to the lamp relay contacts. These two components will make a few milliamperes flow into the lamp filaments, keeping them warm. Of course, a bigger lamp filament won't even start glowing with this small current, but it will stay warm enough to avoid large thermal shocks at each flash. These two components also reduce arcing on the relay contacts whenever they open, and reduce the inrush current whenever they close. So I've kept this board set under observation for a couple more days, and luckily nothing bad happened, so it will be sent back to the owner to be installed in its cabinet. I hope this was an interesting video and that you learned something. If you have any question, use the comment section below.